Hi students, welcome to Vedantu NEET English. I'm Diksha Kaushal, your chemistry master teacher. And today we are going to take some exceptions. In fact, most important exceptions from P block, DNF block and periodic table, as well as like full inorganic chemistry. I'm also going to take up some exceptions from coordination chemistry, because in coordination chemistry, there are only a few exceptions, right? We know that, okay, inorganic chemistry is all about exceptions, and that's why this lecture was indeed needed for you, right? And the same thing I'm not going to repeat in tomorrow's marathon, because that is about the important concepts, right? Okay, there I'm going to take up the concepts. So this is mostly about the cramming part that you have, right? The factual part that you have. So here we are going to talk about facts, not anything related to conceptual thing. Okay, concepts I'll take tomorrow, right? Session for marathon, everything we'll do that tomorrow, right? That will be full chemistry marathon. So if you all are ready for that, then let me know in the chat box. I am better now, feeling better, but yeah, the eyes are still paining a lot. So I firstly thought of canceling the class. Even I canceled the big marathon because I think I was not, it's very difficult to stand for 4 hours with full energy when your eyes are not working, right? So that is the reason I thought firstly to cancel the class. Then I knew that some of you are really waiting for the classes, so that's why I thought, okay, if you are waiting for that, then I know you are just very few days away from NEET 2025. So I don't want to waste even a single day. I don't want you to be like sitting here and then chilling and then relaxing and not studying chemistry. Okay, so that's why I have come up with this lecture, that is inorganic chemistry exceptions. Okay, yes, everybody, thank you so much for your blessings. Thank you so much. That means a lot to me. Now fill this chat box with green hearts and don't forget to like this video, because students, I am taking this session only for you guys. Okay, only for you guys. I specially planned this session today itself, that okay, let's do something for students. So this is what I planned for you. Okay, now I was supposed to take this class on Monday. Then I thought that okay, this 1 hour class I can easily take, and that will actually benefit you, right? Because tomorrow's marathon that I'm going to take, this I will not include in that. Exceptions I will not include in that. So in that way, that will be full revision with this inorganic chemistry exception and the concepts that I'm going to take up tomorrow, right? Okay. Now let us start it without wasting any time, because this session is going to be a very quick recap sessions. First is going to be your coordination chemistry. Okay. In coordination chemistry exceptions, if you see, not too many exceptions you have here, just the single chart will be beneficial for you. So in this single chart, what we are going to study is the exceptions in VBT. Okay, if you must have seen, in sometimes oxalato is behaving as strong free ligand, sometimes ammonia behaves differently. So why that is so, that is not important to you, but when it is so, that is important for you. So let us see, if cobalt 3 positive is bonded, if I say that cobalt 3 positive is bonded with water and oxalate, let's say you have two ligands, let's say oxalate or you have water, then cobalt 3 positive will behave as a strong field ligand here. Okay, it will behave as a strong field ligand, and CO2 positive is bonded with water, then ligand act as a strong field ligand. Now we know that water, oxalato, all these are weak field ligands. But if they are bonded with cobalt 3 positive, these two will behave as strong field ligand. If this is bonded, water is bonded with copper 2 positive, it will behave as a strong field ligand. These are the important points, right? Next is, if nickel 4 positive is bonded with fluoride ion. Now fluoride ion is also a weak field ligand, right? Then acts as a strong field ligand. So if you have nickel 4 positive is bonded with fluoride ion, then it will act as a strong field ligand, right? Next is, if iron 2 positive and manganese 2 positive bonded with NH3. Now NH3 usually behaves as a as a strong field ligand. NH3 usually behaves as a strong field ligand, but with iron 2 positive is Mn2 positive, it is behaving as a weak field ligand. Okay. Next is 3D series elements in +2 oxidation state. If you say 3D series element in +2 oxidation state from outer orbital complexes up to NH3 in spectrochemical series. Outer orbital complexes means D2sp, outer means sp3d2. Now they are saying 3D series element, that is Saktiv, Karman, Fico, Jal, right? The elements of 3D series in +2 oxidation state form outer orbital complexes up to NH3 in the spectrochemical series. So in your spectrochemical series, up to NH3, it will form sp3d2. That means up to NH3, there will be no pairing of electrons. Okay, there will be no pairing of electrons up to NH3. Compounds of platinum, Pd and Au with coordination number 4 prefers dsp2. Now this is a very important thing, right? Compounds of PT, PD and Au, they will prefer dsp2 hybridization with any type of ligand they will have. Any type means it doesn't matter, they have strong field, weak field, it hardly does matter to them, right? Okay, it will always have a dsp2. dsp2 means it will always it is going to be dsp2, there will be no sp3, it is going to be square planar always. So that was about coordination chemistry exceptions. Now I'm going to take up the exceptional trends of P block here, right? Okay, for P block, what we are going to start with, for P block C, you have boron, aluminium, gallium, indium, thallium. Here some of the important trends that you have. I look for all the important exceptions for you here, right? So starting with the, let's see, this is the chart that you have. Here, what are the important points from this chart? First point is atomic radii. This is very important. No matter how many times I teach you, that is less, right? Directly, this question directly they ask you. Idea is that right now I feel that in NEET exam they will ask you in one question, they will ask you multiple exceptions, right, with the help of match the following. Okay, so I think in one question they will ask you 4 exceptions, and there will be definitely, see, if they ask you one question with match the following, that means one question is enough for you, right? So the marks that you are getting, 4 marks, that will be for four exceptions that they will ask you. So definitely there will be one question minimum for exceptions, and if they ask you distributed questions, there can be 2 or 3 questions also regarding the trends exceptional trends here. I am not talking about the exceptional lines, I am talking about the exceptional trends, okay? So here you have, first is atomic radii, that is, it should be Bal Gaye Indian tail. So it should be BALGAINTL. We know that down the group what happens, atomic radii increases. So it should be boron, aluminium, gallium, indium, thallium. But in reality what happens? Here they will have a switch. Over here they will have a switch. And over here, yes, over here they will have a switch, right? That means firstly there will be boron, then will be gallium, then aluminium. Reason is because of the poor shielding effect of d electron. So here answer will be BGAAL, then IN, then TL, right? Next, very important, that is the exceptional trend of ionization enthalpy. So in this case, what you have to remember, that this is going to be, everybody listen to this, very important, right? Write it down in the chat box. Those who remember, write it down in the chat box. That is a revision session, right? So many times we have done the same thing on this channel, right? This is a revision session so that in seconds these exceptions should get clicked in your head, right? So here what you will learn, that this is nothing but it is like W. You will stretch it here. So this is like going to be this kind of W, right? Now you will write it BALGAINTL, right? So here it is going to be, boron, then you have thallium, then you have gallium, then you have aluminium, then you have indium. So that is nothing but 1, 5, 3, 2, 4. You can also remember this point, 1, 5, 3, 2, 4. 1, 5, 3, 2, 4. Firstly, all the odd numbers, 1, 5, 3, then all the even numbers. 1, 5, 3, 2, 4 is the order here, right? Okay. So firstly boron, then you have thallium, then gallium, then aluminium, then indium, right? Down the group ionization enthalpy decreases, but this will be the correct order here, right? Okay. Next is electronegativity. So here what order it will follow, like very weird order. There is no as such trend over here. Again, this they don't ask very frequently, but you can go through this. So basically what is happening here, right? Firstly, you have maximum is boron, right? After that, it is starting from here. Aluminium, gallium, indium, thallium. Okay, that is how you are going to write it. 1, 2, 3, 4, 5. Okay, that is the decreasing order. How you are going to write it? 1, 2, 3, 4, 5. That is order. You know, when you learn these in numbers, that will be easy for you to learn. This session is to learn these things, right? You have so many times you have understood this thing. 1, 2, 3, 4, 5 is the electron negativity order. This they don't ask very frequently, but still I am writing because I have to tell you all the exceptions that are there. Right? Now talking about the oxidation state, remember one question is asked from oxidation state. That is, first you should know one thing, that which is the lower oxidation state, which is the higher oxidation state. So talking about oxidation state, lower oxidation state is Np, right? The number of electrons in P, and higher oxidation state is number of electron in S and P electrons. That is the higher oxidation state. So what you will write here, when you're writing, always remember down the group lower oxidation state stability increases. Just remember this thing. By this thing, you will be able to solve so many questions regarding the exceptional part here. Right? So general oxidation state, because here the electronic configuration of this family is Ns2Np1. Right? So there is lower oxidation state is 1 and higher oxidation state is addition of 2, that is 3. So plus 1 and plus 3 are the two oxidation states here. But down the group, lower oxidation state stability will increase. That means if you talk about thallium, thallium is more stable in plus 1 oxidation state and it is not stable in plus 3 oxidation state. That is the reason thallium 3 positive wants to get converted to thallium positive, and that is the reason here oxidation number decreases. When oxidation number decreases, what you will say? Oxidation number decreases, that means here it is itself getting reduced. It is oxidizing something else. It is a very good oxidizing agent. So they will not ask you down the group it's increasing or decreasing. In any of the groups of your P block, they can pick any element and they can ask you whether this is behaving as an oxidizing agent or as a reducing agent. And this is the criteria to identify whether it will behave as a reducing agent or an oxidizing agent, right? Next is metallic character. We know that down the group, if you talk about the atoms, down the group metallic character always increases, along the period metallic character always decreases, right? There is no exception in that. Melting point is the exceptional trend here. So what is there? This is also important, right? Decreases up to gallium, then increases. Okay, this was also important, right? Decreases up to gallium, then it also starts increases. So you can say that gallium has exceptionally low. Gallium has exceptionally low melting point. Exceptionally low melting point. It does not have very low boiling point. And this question also can be asked. Now, if you talk about the boiling point, it does not have very low boiling point, and that is the reason this point becomes extremely important for you. Wait a minute. Yes, this point becomes extremely important for you. That is gallium with unusually low melting point, that is 303. It can even melt in our palms. Could exist in liquid state during summer. Its high boiling point makes it useful material for measuring high temperatures. Okay, this you have to remember. Okay, always remember this thing. This is very, very important. It has exceptionally low melting point, but the boiling point is not low, right? Okay, then these are normal. Densities, mass increases, so density will also increase down the group. There is no exception in that. Now, with air, you have to remember some important points here. That is, reacts with air to form oxides, right, and nitrides. Both of it will form. Crystalline boron is unreactive and amorphous boron reacts here. Aluminium form oxide layer and does not react further. Okay. Next is reactivity. Okay. If you talk about with air, there are some also other important points, right? Yes, these are the important points. Unreactive in crystalline form, it forms very thin layer of oxide on the surface of aluminium. Amorphous boron and aluminium reacts on heating, form B2O3, and Al2O3. With dinitrogen at high temperature, they form nitrides, right? This is nitride and this is the oxide of 13 group elements, right? Okay. Then, beta, I have picked up some important lines for you. Okay, those lines I am showing you, right? Reactivity with acids and alkalis. If you talk about reactivity with acids and alkalis, boron does not react, right? Boron will have no reaction. Remember this point. Boron does not react, right? Aluminium react with both acids and alkalis to liberate hydrogen gas. Aluminium will react with both acid. That is why aluminium is amphoteric in nature, right? Aluminium is passive with concentrated nitric acid. With concentrated nitric acid, it will have no reaction. Okay. Then reactivity with halogens, they form trihalides. Now here the exception part I am underlining, except triiodide of thallium. That means TLI3 does not exist. Okay, TLI3 does not exist. So everybody spam it in the chat box. TLI3 does not exist. All the trihalides will exist here, right? Okay. Then nature of trioxides, boron is acidic, aluminium and gallium are amphoteric, and indium and thallium are basic in nature. Regarding direct atoms also, they ask you what is the acidity and basicity order here. Now, this is also your NEET previous year question from your NCERT line directly. Due to small size, this is also exception. Why it is so? Due to small size of boron, some of its first 3 ionization enthalpy is very high. This prevents it from forming +3 ions and forces to only have covalent compounds. Okay, if you see other group 13 element will have ionic compounds, right? But here this is only having the covalent compound. Reason is because the first 3 ionization enthalpy is very high, and due to its small size, here easily assertion reasoning question they can ask you from this part of the chapter, right? Okay. Next is the nature of these oxides vary. This we have done already. Nature of the oxides, right? That we have done. Now let's talk about carbon family, right? So this is the table from carbon family. What are the important points? Let us see that, right? So first thing is atomic radii. There is no change, right? Atomic radii is as it is. There is no exception in the atomic radii. But in ionization energy of carbon, you have the change. That is over here, right? It should be SNPB because down the group ionization enthalpy decreases. But over here you will see the jump here, right? This should be SNPB, but it is actually PBSN, right? Next is electronegativity. This question also they have asked, right? So electronegativity decreases down the group, that we know, right? But here what will happen? First you will have carbon, then you will have lead, then silicon, germanium and tin will have the same electronegativity. From the NCERT data, if you see, here carbon is having 2.5, then you will have lead that is having 1.9, then silicon, germanium and tin are having equal electronegativity. That is a very, very, very important point, and this they have asked you. This is very important. This is also very important exception, right? Next is oxidation state. I have already told you oxidation state will be NS2NP4 here, plus 4 NP4 is it? Yes. Plus 4 is the lower oxidation state, and wait a minute. It is having 14, no, then it will be NS2NP2. 14 electrons, 14 is the atomic number. It will have 4 outermost electrons. So 2 is the lower oxidation state. When you add these two, plus 4 is the higher oxidation state. Down the group, the oxidation state, lower oxidation state will increase. From here, the very frequently asked question is that Pb2 positive, Pb4 positive is a reducing agent or an oxidizing agent. So we know that in +4 oxidizing state, we know that that is not stable because that is the last element of this group. That is why lower oxidation state will be more stable. So here it is more stable in Pb2 positive. That is why it is a very good oxidizing agent. That is the reason Pb4 positive is a very good oxidizing agent. Right? Okay. Now, next is the metallic character. There is no exception in that. It increases. Now melting point, let us see what happens. Decreases up to 10, then it starts increasing. If you see here, melting point, here is the exception. First it will decrease up to 10, then slightly there will be one increment. Okay, so melting point also is one exception here that you should know, that here firstly it will decrease, then after 10 to left there will be slight increment, right? Boiling point decreases, density also increases, there is no exception. Now chemical property reacts to form monoxide, dioxide, only tin. Now this is very important. Only tin reacts with steam, okay? Only tin will react with steam. Rest all do not react with water in any form. Only tin reacts in steam. All of them, rest of them do not react in any form. Okay? Understood? Yes. Now, reaction with halogens, react with halogen to form dry halides and tetrahalides they will form, right? Okay. Now, this is the catenation property that also decreases down the group. Catenation property is the self-linking property here, right? Next is PB has no catenation tendency. They can ask you, out of the following which does not have any catenation tendency, that is PB does not have any catenation tendency, right? Okay. Due to property of catenation, p-pi formation, carbon is able to show allotropic forms here. Next is, this paragraph is also very important. These two paragraphs from your NCERT are very, very important. Here what they are saying, the central metal atom in these halides undergoes sp3 hybridization. That is true. Because, and the molecule, because see, if it is, the molecule is tetrahedral in shape, exceptions are SnF4 and PbF4, which are ionic in nature, right? Very important. Now, all of this is they are telling you the central metal in the halides, the tetrahalides, they undergo sp3 hybridization. Like you have CF4, all of these are tetrahalides, right? But SnF4 and PbF4, they are ionic in nature. They can ask you which of the following pair is ionic in nature. So this is directly mentioned in your NCERT. Next, this point is very important, that PbI4 does not exist, right? What are we saying? PbI4 does not exist because PbI bond. So this can be your assertion reasoning question that they can ask you directly, that why PbI4 does not exist? Because PbI bond initially formed during the reaction does not release enough energy. PbI bond, they will not release enough energy to impair 6s2 electrons. That means inner core electrons will not be involved here and excite one of them to higher orbital to form 4 unpaired electrons around the atom. That is the reason PbI4 will not exist only. So these two questions they can ask you, right? Okay. Yes. From here you start. SiO only exists at high temperature. Oxides in higher oxidation state are generally more acidic than in lower oxidation state. That means the acidity depends on the oxidation state that I have told you before also, right? Okay, this you have to see. Then these are the oxides which is directly asked, that carbon dioxide, silicon and germanium oxide is acidic, whereas tin and lead oxide are amphoteric in nature. And if you talk about monoxides, CO is the neutral, GeO is distinctly acidic, whereas SNO and PbO are amphoteric in nature, right? Okay, understood? So this is about the nature of oxides, and this is also a very famous question for your NEET exam that they ask very, very frequently regarding the oxides, the nature, amphoteric character of the oxides, right? Okay. Now, I think this we have done. Yes. Okay. Wait a minute. Let me see. There is considerable increase in the covalent radius from carbon to silicon. Thereafter, silicon to lead. A small increase in radius is observed. This is due to presence of completely filled. So basically, what we have seen, that here down the group, the order is increasing only, right? Okay. But here what exactly happens, zinc and germanium have approximately same radii. So if you see this in the table itself, I'll show you the table here. So if you see the table here, this is the atomic radii, this is the atomic radii, right? So what you will see, carbon and silicon, you will see a very high increment here, right? Then this is silicon and this is germanium. Then it is approximately difference of 4 units, right? Then again it is increasing, then there is also increasing. That means then the increase is very, it's not very sharp increase that you can see after this, right? Okay. Next is the electronegativity that I have already told you. Firstly, carbon, then you will have lead, and these three are going to be less than lead, but they are going to be equal. That is silicon, germanium, and tin, right? Okay. Now, density also is very important. That also plays a very important role here. This trend, very rarely they will ask you this trend, but you should know that density also in carbon compounds that does not follow a simple direct order. Melting point, right? If you see melting point here, I'll show you the order here only, right? This is the, this if you see, density is over here. Density, what you can see, first it is decreasing, then it is increasing, then it is increasing, then it is increasing, right? That is the order of density over here. Then where is the trend of boiling point, and this is the trend of melting point, right? In melting point also we have seen the abnormal trend here. Firstly it is very high, decreasing, 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 then slight increase is there, right? So that you can see in the melting point as well. Right, students? Okay, so melting point and density we have seen here, right? I think I'll delete these two slides. Yes. Okay, now let's move ahead here. That is the ionization enthalpy. This also we have seen. Let me see if there is some important lines for you over here. Right, this we have seen. This also we have seen. Yes, since sum of plus 4 ionization. Okay, now see this. Since sum of first 4 ionization enthalpy is very high, in this case, compounds in plus 4 oxidation state generally are covalent in nature. Generally, they are covalent in nature. We are not saying always, right? Okay, and this exception we have done. These 2 points we have done, right? Yes. Now, let us talk about next table, that is group number 15, right? So in group number 15, 16 and 17, mostly the questions are based on electron gain enthalpy, and there are some important parts that I'll tell you. That is hydrides also is very important in that case, right? Firstly, the name is nitrogens, and here electronic configuration is Ns to Np3. That means the lower oxidation state is 3 and higher oxidation state is 5. And because of the electron negativity, it also can show you plus 3 oxidation, minus 3 oxidation state, right? Okay, that means it can also gain the electron, right? So here what you will see, extra stable electronic configuration to half filled p orbital. That is why it has group number 15 generally has very high electron ionization enthalpies are very high because of the stable electronic configurations, right? And what you will see here, right? If you talk about the properties, atomic and ionic radii, it is increasing down the group due to number of inner shell, right? Ionization enthalpy, there is no exception, it decreases down the group. Electronegativity also decreases down the group. These are the general properties, right? Now let us talk about the important properties here with the help of this chart here, right? If you see that all the elements of this group are polyatomic, like you have N2, P4, S8, not S8, S8 is in next group, like P4 you have, right? So dinitrogen is a diatomic gas where all the other elements are solids in nature. Only dinitrogen is a diatomic gas. The boiling point increase from top to bottom. So when we go top to bottom, boiling point usually increases. Here you have no exception also, right? Melting point has one exception that is important. Melting point increases up to arsenic, then decreases up to bismuth. So I'll just show you the table also here for melting point, right? If you see, this is the melting point. So what you will see, firstly it is increasing, then it will decrease, then it will decrease. So it is increasing up to arsenic, then it is decreasing up to bismuth. There is increment, then there is decrement. This is how it is. Okay, it has this kind of chart for your melting point, right? That's why the question that they can ask you, in group number 15 elements, out of the following, which has the highest melting point? So answer will be arsenic has the highest melting point in group number 15, right? Then if you see, boiling point is sorted, right? Metallic character increases down the group due to decrease in this, that is also sorted. Now next is, except nitrogen, all other elements show allotropy. Allotropy, like phosphorus is white phosphorus, red phosphorus you have. All the other elements shows allotropy, just like you have seen in phosphorus, but nitrogen will not show that, right? That is also one of the important exception. They can ask you, out of the following, which does not show allotropy? So answer will be nitrogen in group number 15, right? Then there is the hydrides. This is not any exception, but they are very, very frequently repeated questions on hydrides. So one thing to understand is thermal stability decreases, and what are the other things that will decrease down the group? Basic character will decrease down the group. Bond dissociation enthalpy, because thermal stability is decreasing, so the bond energy required to break the bond is also decreasing down the group. So these three things are decreasing down the group. And if you talk about reducing character, the acidic character also, that increases down the group, right? That increases down the group. These are the some of the general statements that you should know, which of the following is increasing, which is decreasing. Okay. Next is reducing character or acidic character, you can say, that we have seen. Next is boiling point, right? Okay. So here we have the exception, because NH3 forms hydrogen bonds with itself. That is the reason. So what is happening here? It should be NH3 here, right? Then it should decrease, then it should increase down the group, right? So hydrides boiling point should increase down the group here, but because of the hydrogen bonding in NH3, it will lie somewhere here. It will lie somewhere here. This is very, very, very important, right? And it is very frequently asked. I have seen this so many times, right? Okay. Right, I have seen this so many times that this question has been asked in your NEET exam, right? Okay, next is basic character, that I have told you here also, that will decrease. You don't need to see this separately, right? I will just delete this. You don't need to see this separately. I have already written there, right? Okay, I have already written there. You can also ignore this part here. That is why this happens. This also you can ignore. What you need to remember is those three things that I have written there, and the boiling point exception you should remember for your exam. That's it. Okay, understood? Next we have is reactivity towards oxygen. Chal. Reactivity towards oxygen. All these elements from two types of oxides. Now here one important thing is higher oxide is more stable. Right. The oxides of EU2 of nitrogen and phosphorus are purely acidic, N2O. This is actually no. This is actually not right, so I will not write it here. Yes. Arsenic and bismuth, only a small increase in the covalent radius is observed. This is due to presence of completely filled DNF orbitals in the heavier elements. So what you have seen here, like this is your exception part, right? So this is the covalent radius. It is increasing, increasing, increasing. So here what we can see, this increment, right? This increment from here, this is from 70 to 1110, right? Then you have 1110 to 121. After that, the increment is slightly decreasing here, right? This is what they are saying, that the increment decreases, right, after arsenic, right? Okay. Ionization enthalpy of this, there is no exception within the group. But one thing to remember, that if you compare, we know that along the period, this is group number 13, this is 14, this is 15, this is 16, right? So we know that along the period group, what will happen? Down the group, the ionization enthalpy decreases. Along the period, it should increase. That means group number 15 should have less as compared to group number 16. But in reality, group number 15 has more ionization enthalpy as compared to group number 16 also. Reason is their half-filled stable configuration, right? Okay, much greater than group number 14 due to extra stable p orbital, right? That is there, right? Okay. Now, electronegativity, right? Here it is decreasing, but these two last one are the antimony and bismuth have the same electronegativity. Next one we have is melting point that I have shown you, that it firstly increases from nitrogen to arsenic, then it will start decreasing till the end. This is very, very important that I have already told you, right? This also we have seen that the boiling point in general increases from top to bottom, but melting point increases up to arsenic, then decreases up to, like boiling point does not have any exception. Melting point has the exception. Again and again I am saying, if they ask you the boiling point, that is same, right? Boiling point in general increases from top to bottom in group, but melting point has this exception. Remember this, you can get confused in the exam regarding this, right? Okay, now regarding some reactions here that are mentioned, the important reactions. In the case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solution. These kind of questions also they ask you, which of the following cannot disproportionate, which of the following can disproportionate. In case of nitrogen, all oxidation state from +1 to +4 can disproportionate in acid solution. For example, this. So here, what is the state here? This is 1 plus x minus 4 is equals to 0. So x is equals to +3. So here nitrogen is +3 state. Here it is 1 plus x minus 6 is equals to 0. So x is equals to +5 here, right? Here it is x minus 2 is equals to 0. So x is equals to +2. Here it is increasing. Here it is decreasing. So that means nitrogen is getting disproportionated in these three oxidation state. Either it can be +1, +2, +3 or +4. If any of this oxidation state it has, in acidic solution it will get disproportionate. But in case of phosphorus, nearly all intermediate oxidation state disproportionate into +5 and +3, right? In phosphorus there is no condition that it should be there, this particular state should be there. All of them will disproportionate into +5 and +3, the intermediate states we are talking about. However, in +3 oxidation state, in case of arsenic, antimony and bismuth becomes increasingly stable with respect to disproportionation. But in case if you have +3 oxidation state in arsenic, antimony or bismuth, it will not be disproportionated, right? Okay. Next is NN bond is weaker than single PP bond because of inter. Now this is a very, very important point, very, very important point, right? Remember beta, one thing remember, when you talk about carbon, then you talk about carbon, nitrogen, oxygen, then fluorine. Okay. Here, if you see, in all these cases, right, this is Ka, C, Na, P, oxygen, sulfur, and here it is chlorine, right? See one thing. Always we know that down the group size increases. So what exactly happens? Size is increasing, size is increasing. Size is increasing, that is why to break this bond it will be difficult. So that is why bond dissociation energy will be more for this one than for silicon, because it is smaller in size. But in case of nitrogen, oxygen, fluorine, it is opposite. Can you tell me why? Down the group, ma'am, size is increasing. So that means it is easy to break the bond, but you are saying it is difficult to break the bond. The bond dissociation energy, you are saying it is bond dissociation energy. I am saying it is in these three cases, it is increasing. Reason being, here you have one lone pair, right? Here you have two lone pair. Here you have three lone pairs. So that is the reason, because of this electronic repulsion, right? the bond will become weak, and hence it will be difficult to break this. It will be difficult to break. Wait a minute. This bond as compared to this bond. Okay, so this is what they have written. NN bond is weaker than single PP bond. Here we are talking about single bond only because of high interelectronic repulsion of non-bonding electrons owing to small bond length of. Bond length is small, electronic repulsions is there. That is the reason. Okay, that we should always remember. Here we are talking about the single bonds, right? Basicity decreases, this we have seen. Due to high electronegativity and small size of nitrogen, NH3 exhibits hydrogen bonding. That is the reason NH3, the boiling point, solid as well as liquid shape. Because of this, it has higher melting and boiling point as compared to PH3. This question also they have asked so many times. Okay, this is the general data. You don't have to remember the data. You should remember the melting point, boiling point, the dissociation energy, angle, all of this, right? If you see bond dissociation energy, if you see bond angle, if you see bond angle is decreasing only. So you should remember from NH3, PH3, arsenic and antimony, it is decreasing down the group. So you can write here bond angle of HEH that decreases, right? And if you talk about the formation, like that is increasing. To form this compound, they will hardly ask you. Mostly they will ask you the dissociation energy that we have seen, it also decreases because stability decreases. That is why dissociation energy decreases here. Because to dissociate the bond, it is easy. That is why it is easy to dissociate the bond. That is why bond dissociation energy is decreasing. Stability is increasing. Because stability is increasing, that is why to make this bond, it is easy. So it is formation is increasing, right? Distance, if you say, distance is also increasing because down the group, the atom, the size of the atom is increasing. So the distance will also increase, right? Boiling point and melting point is very, very important for you, right? Boiling point, if you see, it is decreasing, then it is increasing, then it is increasing, then it is increasing. Right? If you want to write it down, so when you have, this is between 238 is between over here, right? This is your NH3 over here. That means here you have PH3, then you have arsenic, then nitrogen, then antimony, then you have bismuth. Okay, that you should remember that how it is happening. First you have phosphorus, right? Then you have arsenic, then you have NH3, then you have antimony, then you have this. Okay, what about this thing here? It is decreasing, then increasing, then increasing. So here what you will write, maximum is for NH3, right? Then you have antimony, then you have arsenic, then you have pH3. Okay, so this is the order of melting point here. Right, this is the order of melting point that you should remember. Okay, yes, everybody understood? So these are the two orders that you should remember for boiling point and the melting point. Okay, that I have written here. Now, let us see the next one. Let us see the next one. Okay. All the trihalides of these elements except those of nitrogen are stable. Now here important thing is NF3 is known to be stable, right? So only NF3 is the stable compound here. What we are saying, all the trihalides except for those nitrogen are stable, right? Nitrogen trihalides are not stable, right? You will not see NBr3 does not exist. NCl3 does not exist, and I3 will not exist. Only NF3 is known to be stable here, right? Okay, only NF3 is known to be stable here. That is the important point, right? Okay, now we have group 16 elements, right? In group 16 elements, this is the table chart, right, directly from your NCERT. Now let us see what you have to remember here. The electronic configuration is Ns2Np4. That is the reason the lower oxidation state is +4. higher oxidation state is +6, right? And it also has -2 oxidation state, that after accepting -2 electrons, it can also become NP6. So that is also possible in this case, and that decreases down the group, right? Because electronegativity decreases, and this state is due to the tendency to gain the electron, right? The tendency or stability of +4 oxidation state in comparison to +3 oxidation state increases down the group, because lower oxidation state stability increases down the group. Now let us see some of the important points of the hydrides here. So we know that the thermal stability, I'll write everything here: thermal stability, the basicity character, the basic character, the bond association enthalpy, all of that decreases down the group. The acidic character, the reducing character, that increases down the group, that you should remember, right? Next is the boiling point and the acidic strength we have seen, right? Boiling point, again, because oxygen and in water also there is hydrogen bonding. That is the reason H2O has maximum boiling point here. What we know is it should increase down the group. Water should have minimum boiling point. But because of the hydrogen bonding, water has the maximum boiling point here. Right? Okay. Next is reactivity with oxygen. So ozone and sulfur dioxide are gases, while selenium dioxide is a solid. Reducing property of dioxide decreases from SO2 till beryllium. SO2 is reducing, while TeO3, this is a very, very important point. SO2 is reducing, while TeO2 is oxidizing in nature. Can you tell me why? Because here sulfur is in +4 oxidation state and Te is also in +4 oxidation state. We know that in higher oxides, what exactly happens? Lower oxidation state is stable down the group. So here what will happen? This is TeO2 is oxidizing. So basically what you have here, this is what you have. So down the group, we know that its oxidation state obviously decreases, right? So here what can happen here? It would want to go in the higher oxidation state, right? Okay. So that is the reason its oxidation number is increasing, right? Itself it is getting oxidized, and that is the reason SO2 itself it is getting oxidized, so it will want to reduce something else. That is why it is reducing in the nature, right? That is why it will get reduced in the nature. That means it will try to reduce something. It itself is getting oxidized, so it is why it's very good reducing character it has, right? Then you have, besides CO2, sulfur, selenium and beryllium also form EO3 kind of oxides, right? Both kind of oxides are acidic in nature. Next is electron gain enthalpy. This is a very, 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 very important question that is very importantly frequently asked, right? So we know that what exactly should happen. Down the group, electronegativity should decrease. But oxygen has, if you say, down the group, down the group, it should decrease. It should be like this. Oxygen should have maximum electron gain enthalpy. But oxygen, because of its very small size and 3 lone pairs around it, that 2 lone pairs around it, that is why it has the minimum electron gain enthalpy because of the electronic repulsion. And this order is very, very important. Reason I have told you, because of the electronic repulsions here, right? Okay. Next is we have ionization enthalpy. The elements of this group have lower ionization enthalpy. Why? Because if you have NP4 here, after losing it will be in the stable electronic configuration. That is why they have the lower ionization enthalpy as compared to group number 15, right? This is about the hydrides. If you just look for melting and boiling point, that is the important part for you. Melting point we know maximum is for H2O. I'll just write it here, H2O. Then you have H2TE, then you have H2SC, then you have H2S, right? That is the melting point, right? Talking about the boiling point here, here you have H2O, right? Then you have again H2TE, then you have H2SC, Then last is H2S. That is the order for melting and boiling point that you should remember, very, very important, right? Regarding the distance, size increases, distance also increases. Angle also is decreasing down the group because the size is increasing, right? Enthalpy of formation, stability is decreasing. That is why, stability is increasing. That is why it is easy to form that compound. So here, wait a minute, enthalpy of formation will increase. Yes, okay. So dissociation enthalpy. See, dissociation means down the group. When you dissociate enthalpies, you can directly write it that dissociation enthalpy increases here because the stability is increasing. No, so if the stability is increasing, dissociation enthalpy also will increase, right? Okay, dissociation constant, you don't need to learn this dissociation constant here. That is nothing, right? Next is reactivity, reactivity towards the halogens. Okay, now this reactivity is towards the halogens. Let us see that reactivity towards the halogens amongst hexahalides, that is hexafluorides are only stable halides. This is very important. Hexafluorides are only the stable. Sulfur hexafluoride is exceptionally stable for its steric reasons. Also very, very important, right? They can ask you regarding some important lines also, and these are the important lines. Okay, next is all elements except oxygen form dichlorides and dibromides, right? Okay, all elements except for oxygen does not form dichlorides or dibromides. All the other elements, right? SCl2 you will see, but OCl2 you will not see. OBr2 you will not see. So oxygen will not form, except oxygen form dichlorides and bromides. These dihalides formed by sp3 hybridization thus have tetrahedral structure. Well-known monohalide structure. See, if you see here, there is no oxygen over here. These dimeric halides undergo disproportionation as given below. They can also undergo disproportionation reaction here, right? Last is for halogens, right? Then there is halogens, right? So in halogens also there is 3-4 things that they very, very frequently ask. I'll just tell you what are these things. So first is regarding the covalent radii is not like it is increasing only, like simple thing. Ionization enthalpy is also simple here, not so complicated here, right? But one thing that you need to remember is electron negativity here. Fluorine has 4 electron negativity, it is decreasing here. Melting point, if you see, melting point is exactly increasing. Boiling point is also increasing down the group. There is exception in the electron gain enthalpy, that is very, very important. Bond dissociation enthalpy is very important here, right? So atomic radii, it is increasing, right? So ionization enthalpy, this is important, right? Yes. Okay. So fluorine, chlorine, bromine, iodine increases down the group. Electron gain enthalpy, this is very, very important. We know that electron gain enthalpy, I'll also write it over here. Electron gain enthalpy should be fluorine, chlorine, bromine, iodine, right? Electron gain enthalpy down the group should decrease. It should be like this. But fluorine has minimum, not minimum, fluorine will replace this situation and it will be over here. So it will be chlorine, then you will have fluorine. So fluorine, because of its electron negativity, has like it wants to gain the electron, but because of the small size of the electronic repulsions, it is not able to gain the electron with maximum efficiency if we compare it with group number, if you compare it with halogens, right? So that is why this will become the correct order. Then there is bond dissociation enthalpy, that is very important. So these two orders are very, very repeatedly they ask you these orders. Now here the same thing. Bond dissociation enthalpy, we know that this is F2, then you have Cl2, then you have Br2, then you have I2. It should decrease down the group, right? Because fluorine is smaller, it should have maximum enthalpy, bond dissociation enthalpy. But because of the electronic repulsion, the bond, as I told you, in nitrogen also, oxygen also. Similarly, in fluorine also, because of the small size and 3 lone pairs, it will become very weak, and hence it will be, first you will have fluorine, then bromine, then you will have fluorine, and then you will have iodine, right? This is also a very, very, very important order. Very, very, very important order. Okay. Next is non-metallic character, right? Decreases down the group. Iodine shows distinct metallic properties, right? Okay. It shows distinct metallic properties here, right? It opposes metallic cluster and form positive ions, right? That is true. Negative electron gain enthalpy. This, students, we have seen this. This is just the explanation that I told you. Why fluorine does not have the maximum electron gain enthalpy and why fluorine does not have the maximum bond dissociation enthalpy. These are the reasons. That was about the electronic repulsions, right? Now, if you see here, very, very important points regarding fluorine, that is, fluorine oxidizes water to form oxygen, whereas fluorine and bromine react with water. Now, there is some different point in this reaction that fluorine oxidizes water to form oxygen. Fluorine with water, it will form oxygen, O2. So, it will oxidize the water, right? It is such a good oxidizing agent. That is why it's such a good oxidizing agent. Whereas fluorine and bromine react with, when you have fluorine and bromine here, they will react with water to form corresponding HX and HOX. That is hydrohalic and hypohalous acid, they will directly form here. They will not oxidize water, right? And what iodine does, it does the opposite of fluorine. The reaction of iodine with water is non-spontaneous. We forcefully have to do this reaction. I negative can be oxidized by oxygen in the acidic medium. That if you have I negative here, I2 will not react with water, but I negative with the water, what you can get is I2. That means it will do the opposite of what fluorine. Fluorine is oxidizing water to O2, but I negative is with O2, it is getting oxidized, right? So it is getting oxidized to I2 here. That is very, very important, right? Okay. Next is the reaction towards hydrogen that we have already told you, right? I have told you all the melting point, boiling point. For this, have we done? I think for halogens we have not done. Okay. For halogens we have not done, right? So for halogens you can see this. Melting point and boiling point is different. All the others are same. Bond length is increasing down the group. Bond dissociation, if you see, bond dissociation enthalpy is also decreasing. So I'll just write here bond dissociation enthalpy, thermal stability, basic character, that will decrease. Acidic character, that will increase. Okay, acidic character of reducing power will increase here. That you can see here, right? This is all given in your paragraph form. They react with hydrogen to form HX, but affinity for hydrogen decreases from fluorine to iodine, right? So that means stability here will decrease here. Stability decreases, no? Wait a minute. Thermal stability, if I'm saying it is increasing, thermal stability is decreasing, so bond dissociation enthalpy is also decreasing. Yes. Some of the properties of hydrogen halides are given in the table. The acidic strength of these varies according to the group, that is this. Acidic strength is what? It is it is increasing because the length HF is smaller, HI is bigger. That is why it is easy to give off H positive, right? The stability of these halides decreases down the group due to decrease in the bond dissociation enthalpy in the order of this. Bond dissociation enthalpy is decreasing, so stability is also decreasing here. Now coming to the melting point and boiling point here, these are very, very important. Melting point, as you can see, I'll just write it here. Melting point is maximum for HF. Then you have it is maximum for HI. Then you have HF. Then you have HBr. Then you have HC. Right? This is how it is. Right? And talking about the boiling point here, boiling point, I'll write it here. These are very, very important exceptions from your tables that you usually ignore, right? That's why from table only I am picking up. So this is maximum is for HF, right? Then you have for HI, same order it is, right? Then it is for HBr, right? Then it is for HCl, right? Okay. Melting boiling point order. You know what is the reason? Reason is the small size of HF, small size, and forms hydrogen bond. That is why its melting point cannot be minimum. In reality, what should happen? Down the group, it should increase. It should be HA, then HBr, then HCl, then HF should have minimum, right? Melting and boiling point. Because of the hydrogen bonding, it will lie somewhere here. It will lie here. So that is why it is HI, HF, HBr, HCl. Understood? The reason is same, but the order is quite different. In NH3, that will land to the third position, right? From last, it will land to the third position. In H2O, from last, it will land to the first position. But in case of HL, it will land somewhere here, right? Okay, wait a minute. HI has a maximum row, yes. So this is the order. Here the order is quite different. Here you have HI maximum, here you have HF maximum. Okay, order I have given you. From NCRT only we are picking the orders, okay? So we can't pick orders from Google, okay? Don't pick orders from Google, ma'am, it was this given in this book, that book. Pick what is given in your NCRT. This is a table of NCRT. In some books, this may be written, maybe for boiling point and melting point, they would have written the same order, but you should follow NCRT, not Google, okay? Maybe Google is correct, but you have to follow the latest NCRT, right? Okay. Then there is this next chart is for group number 18 elements, right? So they have the maximum radii. Now let us see what are the basic. There is no exception in this, but still a general electronic configuration except helium, which has 1s2. Ionization enthalpy decreases. Stable electronic configuration, they are very high ionization enthalpy because fully filled electronic configuration they have. Totally inert gases they are. Atomic radii increases down the group. They have no tendency to accept electron and therefore have very large positive value of electron gain enthalpy. That means their electron affinity is negative and their electron gain enthalpy is very highly positive. That means they require a lot of energy if you want to give them any electron, right? Okay. Then exceptions are about electron gain enthalpy only, that they have the maximum very highly positive electron gain enthalpy, right? So this is firstly among them also neon has maximum, then argon, krypton, xenon, radon, then you have helium, right? Physical properties has lowest boiling point of any known substance. Lowest boiling point, that is the exception first thing. It has unusual property of diffusing through most commonly used laboratory materials such as rubber, glass or plastic. Right? Okay, these were about the physical properties of noble gases. Then along the period, some exceptions that you should know along the period. That is here, I think this is for the radius, right? This is the atomic radius. Okay, this is the atomic radius. That we know that along the period radius should decrease, but neon has the maximum. That means halogen noble gases has the maximum because of the van der Waals radius. They don't form compound with itself, but they form compounds with different molecules. That is why they have very high van der Waals radius. Ionization enthalpy, if you see, this is regarding the second period, very important. This also they have asked so many times this question. One thing is, firstly you have, it should be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, right? So it should be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. It should increase or decrease. Along the period, it should increase, right? It should be like this. But in reality, what will happen? Because this beryllium has 1s2, 2s2. This nitrogen has 1s2, 2s2, 2p3. They both have stable electronic configuration, So beryllium, it is difficult to take out electron, and from nitrogen it is difficult to take out electron as compared to oxygen. That is the reason this will be the correct order. Okay, that is the reason this will be your correct order. Mark it important here, right? Ionization energy of 3D series, this is also very important. We know that along the period, ionization enthalpy is increasing. So it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But in reality, what will happen? This is ionization enthalpy, no? In reality, in front of V coni, you mark opposite, okay? In front of, you just write V coni here, right? Just write V coni. In front of V coni, you mark opposite, so answer will be V, then you have co, then you have ni. So here you have the opposite, rest of them the signs are same. Rest of them you can see the signs are same. So in front of V co ni, you mark the opposite sign, that will be your order. Okay, that will be your order. Okay, yes, I think that's it. Electron affinity, if you see, this is not very important for you for along the periods, but you should know this, that lithium, then you have beryllium. Firstly, it will increase. Lithium maximum, then it will be beryllium. Then boron will have more. Okay, then again it will increase. Similarly to sodium, magnesium, aluminium also it is sodium, then it is decreasing, then again it is increasing. Right? In this case also, here it is fluorine, oxygen, carbon, lithium, beryllium, nitrogen and neon. These are the three very, very important electron affinity values. Okay, electron gain enthalpy you can see, right? So this has the maximum tendency to, like, affinity means want to gain the electron. Otherwise, these are not like very frequently asked to you, but these exceptions are there. But till now, they have not asked regarding along the period electron affinity values, right? Okay. Now, the last part of this session is DNF block. In DNF block, some important exceptions we will see. Already we have seen for 3D series here, the radius. Now we will see the important exceptions here. So these are the important exceptions, especially this is PD. This is a very, very important exception where you have 5s0 here. Only this element has s orbital 0. Others you will have either 1 or 2 electrons. These two are the exceptions. These are the exceptional electronic configurations that you must remember. You can take a screenshot and do it after the class, right? Okay. Next is regarding the melting and boiling point. You should remember this question also they ask you, right? Peaks you should remember. Peaks are tungsten. Peaks you should remember, which has the highest melting point among them. Tungsten, molybdenum and chromium, they have the maximum melting point among them. Then if they ask you the sudden decrease, that is in technetium and in manganese. Sudden decrease is also there in technetium and manganese. These are the two important exceptions from your table. That is not written anywhere, right? But you should remember this from the chart itself, right? Okay. Now this I have told you. Next one is the 5D and the 6D series. 4D and 5D series almost have same radii, right? 4D and 5D series, that is due to the lengthenoid contraction, that you should remember. Because of the lengthenoid contraction, they have approximately the same radii. Then the next question is regarding fluorine and oxygen. So the exception is that manganese, if you see, with fluorine it is existing in +4 oxidation state. But when you talk about with oxygen, it is existing in +7 oxidation state. You can also find it out. 2x minus 14 is equals to 0. It is existing in +7 oxidation state. Reason is because oxygen can form multiple bonds. That is the reason. Oxygen can form multiple bonds, that is double bond. That is the reason with oxygen it can exist in higher oxidation state. Okay, understood? This I have told you that the transition metals, with the exception of zinc, cadmium, mercury, are not the transition elements, right? Because they have fully filled d orbital in excited and the simple state, right? are very hard and have low volatility. Their melting and boiling point are high, right? Okay, so if you see, the high melting point of these metals are attributed to inter-involvement of greater number of electrons from n-1 d orbitals, right? In every row, the melting point of these metals rise up to maximum in D5, except for anomalous value of manganese and technetium falls regularly as the atomic number increases. Now, they have given you that manganese and technetium, it is C. In all, the regular trend is they will fall to maximum when they have the stable electronic configuration. In all of this will have D5, this will have D5, this will have D5. But the exception is technetium and manganese that I have told you, right, fall regularly as atomic. They have high enthalpy of atom. Now, atomization they have asked so many times, right? This is a very, very important trend that they are asking you, enthalpy of atomization, okay? So, high enthalpy of atomization, which are shown in this figure. So, enthalpy of atomization we will specially do. The maximum about the middle of each series indicate that one unpaired electron per d orbital is particularly corresponding to the melting point here, right? Okay. Now, from this table in your NCRT, every single thing is important for you. So, we will study this table, every single thing. So, first is atomic number, that we know, electronic configuration we know, right? Enthalpy of atomization, first you should know that what is the order of enthalpy of atomization here. So, I'll just write the order here. The maximum order, I have already written it so many times, okay, but still I'll write it, right? So, it is maximum in case of vanadium. Then you will have, after vanadium, what you have? 470, then you have maximum, then you have titanium, right? Then 444, you have 430, that is you have nickel. Then after this you have cobalt, right? Then after this you have iron, right? Yes. After this you have chromium. This is very important. You should know this enthalpy of atomization. Right now, very high chances they will ask you enthalpy of atomization, right? So chromium, after chromium is what? Chromium is 390. This we have done, right? Then there is copper, right? Today we will learn this also, okay? We will learn this today. Scandium, then you have zinc, okay? We will learn this also, right? First you have Vitini. Anybody, any order that you can make here out of this? Nico, coffee. We can make coffee here, okay? Vitini coffee. There is some name of coffee. Vitini coffee. Karpu, scandium, zinc. Okay. Now I told you three things. Vitini coffee. The name of the coffee is Vitini coffee. Now you have to make it after this, right? What you can make, let me know in the chat box. Okay. What thing you can make out of this, right? Now ionization enthalpy, right? The trend we have already seen. They will ask you the first ionization enthalpy trend only. Otherwise, they will not ask you ionization enthalpy. Otherwise, which will have more ionization enthalpy, that will be dependent on the stability. One which have half filled orbital will have more, half or fully filled, they will have more ionization enthalpy. This trend you don't have to remember, just remember the 3D series first ionization enthalpy trend, right? Then talking about all this, if you talk about the density, it is increasing. So there is, yes, it is what you can see in density, it is increasing. But with nickel, in density also I am writing, because surprisingly sometimes they ask you some questions, okay? And here it is decreasing. It is less than, it is more than zinc. Zinc has less density, it is increasing, but in the end it decreases very slightly. Okay, that you should remember, right? Okay, yes, I think that's it. Then the last chart here what you should remember, these things here, 1, 2, 3, then this one, then from here you will have, this is, where it is, 7, yes, this one and this one. Okay, these are the things that you should remember, that terbium 4 positive have half filled, right? Cerium 4 positive has 0 electronic configuration. Lanthanum has plus 0, and then you have gadolinium has 0 in 3 positive state. Then lutetium has 14 in 3 positive state. Ytterbium in 2 positive state is 14, and terbium, europium, terbium we have seen here. Europium in 2 positive state, it is half filled. So all the half filled and fully filled stable and 0 electronic configuration state I have mentioned here that you should remember, right? Okay, I think that's it. This is the important part, that is a noble gas configuration. For example, cerium 4 positive will have 4s0, right? Then half filled and fully filled, if you say these two, europium 2 positive and terbium 4 positive have half filled, and ytterbium 14 is with the 14 electronic configuration is for ytterbium 2 positive and lutetium 3 positive. You can also add lutetium 3 positive here, right? This also has fully filled electronic configuration. These are the important electronic configurations that you should remember, right? Okay, and that's it, students, that's it. And all the students who are like looking for good offline coaching, then Vedantu is providing you really good offline coaching. So here are the centers of Vedantu, as you can see over the screen. And if you're looking for any scholarship here, so 40% scholarship we are providing you on JEE and NEET courses. And if you talk about, ma'am, I want to get 90% scholarship here, then you can enroll yourself for IV SAT programs where 90% instant scholarship will be provided to you. 90% instant scholarship, right? So here you just have to register yourself to the admission test that will be taken according to your marks. You will be provided with the scholarships, right? Then for NEET 2025 aspirants, we have NEETpedia where free study material we are providing you. And right now, Mega Revise-a-thon is going till 29th of April, students. In the description, you also have the links that I am, all the things that I am giving you. You have links for that. I'll also show you in the description, right? So pre-NEET 2025 test series is also going on. That is also totally for free of cost. Then free NEET 2025 study buddy, as you can see over here. Just you need to scan this QR code and you will get access to free study buddy, which will help you for your revision. Okay. So guys, that's it for today. Bye bye. Take care. See you all in tomorrow's marathon. Bye bye. Take care.